Hello everyone. So in the previous video, we introduced the sequential design and flip-flops, and we understood the theory behind it and everything. So now we're going to start to implement today's lab using Logisim. The objective of today's lab is to become familiar with sequential design, and this is what we've seen in the previous video, and we studied the different types of flip-flops. Now, we're now going to implement everything that we studied using Logisim and then simulate GK flip-flops and also a 2-bit incrementing counter using GK flip-flops. Now here is just a summary of everything that we discussed in the previous video. Most importantly, we want to understand how does the GK flip-flop operates or works. Now we've seen that when J equals to 0 and K equal to 0, the Q next will not change. The output will still be Q. And we've seen that when J is equal to 0 and K is equal to 1, then the Q next will be resetted. So it will be equal to 0. And when J is equal to 1 and K is equal to 0, the Q next will be set to set, which simply means 1. And when both the input J and K are equal to 1, Q next will equal to Q naught, which is Q inverted. So in case of, let's say Q was previously 0, then when the input is 1, 1, the output will be 1. And if it was 1, it will be 0. So simply we are just inverting the Q for Q next. Now this is everything that we've seen in last video. Now we want to start implementing. Now before I start, I want you to read this lab very carefully on your own because it has some also guidelines for the report. As you know, you have 4 reports. So you did already lab report 1 and 2, and this week you're going to start with lab report 3, and then you're going to have your final one. Now lab report 4, which is the final one, is going to include lab 5 and 6. And lab report 3, which you're going to start this week, is going to be about lab 4 only. So you will see here some hints about the report. For example, for lab 6, for lab 5 and lab 6, when you want to write the report, there are some expectations that I have that you will find in the notes here. For example, here I'm saying that in the introduction of your next report, which I mean your final report, report 4, you are expected to introduce the concept of sequential circuits. So you can use the video, and you can also use other references to also explain and introduce the concept of sequential circuits and all the flip-flops that we taught in this lab and how they work. Now, it's very early for this report because next week you're going to start with lab report 4. But keep in mind when you want to write your final report to go back to this lab sheet and read all the notes that I have left for you. Now let's look at the experiments for this week. For lab 5, we have 3 different experiments. The first one is we want to experiment with GK flip-flop, and we simply want to connect a GK flip-flop using Logisim, and then we will verify the GK flip-flop behavior mentioned above, which is simply mentioned in this introduction. And we want to see when we implement the GK flip-flop using Logisim, are we going to have the same outputs when we have these inputs? So we're going to see today how this is going to work. Now, moving forward, we also have 2 other experiments. The second one, we have to construct a D flip-flop from a JK flip-flop, and we've seen how we did it in the theory video. But now we're going to also try to do it using Logisim. And again, you're going to see here some hints for your lab report. For example, here I'm saying that make sure to include all the design steps in your report, starting from the characteristics tables, K-maps, Boolean equations, and design, and so on. So everything that we discussed in the video must be in your report as well. And finally, we're going to design a 2-bit incrementing counter using a GK flip-flop, also using Logisim. So now I'm going to start with the first experiment, which is simply connecting a GK flip-flop on Logisim. So I want you all now to open Logisim, and then we can start to implement this exercise. So this is Logisim. Now we want to implement a GK flip-flop. So this is going to be our first time using a sequential circuit. So far, we've only studied about the combinational circuits and the basic circuits and so on. So now I want to use Logisim to implement GK flip-flop. Now, the first thing that you have to do is you have to look where like the GK flip-flop is located in Logisim. All the flip-flops are located in the memory folder. So if you expand it, you will find all the flip-flops that we discussed today. And today we want to implement the GK flip-flop. So simply I will just drag the GK flip-flop and I'll have it here. Now I know that the GK flip-flop have 2 inputs and 1 clock input. So I'm going to add 2 inputs. And I need another input. And I know that I have 1 output. And this is something new for you. We also have a clock, right? The GK flip-flop has a clock. So I'm also gonna insert a clock here. Now, where can you find the clock? It's in the folder that's called wiring. So if you expand it, you will find also some new pins that most probably we're going to use in this lab and other lab. So we are looking for the clock, so I'll simply drag one here. And now I'll start connecting. So J is an input, and K is also an input. Now this diagram might not be very clear, but here it simply has, so let me draw it for you. It simply has a J, which is an input K, and there's this inverted triangle, which simply means the clock, and here is our Q, which is the output. So now I want to also connect the clock. So it will go here. And now finally, I want to connect the output to the output pin. So now I want to verify if JK flip-flop is working fine. Now let's remember the truth table for a GK flip-flop. So I have J, I have K, and I have Q, or Q next. So I know that when J and K are, both of them are equal to 0, Q is going to be on hold, which means it's not going to change. Whatever the value that was in Q, it will still be the same, so nothing will change. And also I remember when J is equal to 0 and K is 1, my output should be 0, which is simply reset. And when J is equal to 1 and K is equal to 0, my output is 1, which is simply set. And when both of them are equal to 1, my output was Q naught. So whatever the value of Q, it will be inverted. So now let's test the behavior and see if it's going to give me the same output that I'm expecting. Now, when J is 0 and K is 0, I'm expecting the Q not to change. So Q is 0. So let's see now what will happen. Now, how can I make any changes in GK flop? If you remember that the changes in the flip-flops take place on the clock edge. So in this case, I have to add 1 clock cycle. So whenever there's 1 clock cycle, now I expect some changes. So let me now have 1 clock cycle. As you can see, I have now 2 clock cycles, 3 clock cycle. My output is still 0. Why? Because if I have J and K, both of them are equal to 0, my Q will not change. There will be a hold of the value. So 0 will still be 0. Nothing is changing. Now, let me see what will happen when J is equal to 0 and K is equal to 1. So now J is 0 and K is 1. Now, the output should be 0. So let me add 1 clock cycle. So simply I'll press on the clock cycle pin. And as I can see, my output is still 0 because it's still in the reset state, so it will not change. Now, when j is equal to 1 and k is equal to 0, now I'm expecting my output to be 1. So to make this change, what do I need? I also need to add a clock cycle because I know that the changes will take place on the clock edge only. So now if I added, now do you see my output is finally equal to 1 because j is 1 and k is 0. So now it's the status is set. So it's uh, regardless how many times I add the clock cycle, it's still going to give me 1 because the inputs are 1 and 0. Now, if j and k, both my inputs are equal to 1, then I expect that the output will be q naught. So in this case, my q is 1. So now if I add one clock cycle, it is 0 now. Now if I add another clock cycle, it's 1. So whenever I add a clock cycle, whenever the input is 1, like both of them are equal to 1, my output will be the invert. So when it's 1, it will become 0. When it's 0, it will become 1. We can try it again. Now q is 1. So if I add a clock cycle, now it's 0, another clock cycle 1, and so on. So this verifies the behavior of the GK flip-flop. Now you are required to try it on your own, try to implement the GK flip-flop, and then of course you have to add it, to add a screenshot to the Word file, and then when you have all your screenshots, you're gonna upload. But always remember that we should always label. So this would be J, this will be K, and this is simply my clock. I can call it clock. And this is Q, my output. And also I can add my name here. And then you can now take a screenshot and add it to the Word folder. So by now we solved the first exercise. It's very simple, just about understanding how the GK flip-flop works. Now let's look at our second exercise. So our second exercise is to construct a D flip-flop from a JK flip-flop. So I'm expected to use the GK flip-flop to work as a D flip-flop. And if you remember in the previous video, we saw how this worked, and it was very simple. It was just by adding a NOT gate. So now let's see how this will look like in Logisim. Now, as I said, I just need the GK flip-flop, and I already did it for the other exercise, so I can just edit this to change it to be working as a D flip-flop. By the way, if you go to the memory, we actually have a D flip-flop. Like I can use it, but this question is specifically telling me that implement the D flip-flop using GK flip-flop and not the D flip-flop. So please don't use it, just keep it at GK flip-flop. Now, we've saw earlier in the other video that if I want to convert a GK flip-flop to a D flip-flop, I simply need just to play with the input. So my J did not change, but I added a NOT gate. So I will simply remove also this input, and I'll just add a NOT gate. And then I need my wires here. And this is really simply the answer. So the clock will stay the clock, the J is still the same, but K was J inverted. We've solved it in the previous video with the theory and the explanation. So this is simply how I would implement the flip-flop using a GK flip-flop. So I just added, so the only change that I have that J is the same, but K now equals to what? J naught. Now this should work as a what? A D flip-flop. Now, if you remember, the D flip-flop, the way that it works, it simply give Q simply equal to D. So if D is equal to 0, then Q will be 0 as well. And if it's equal to 1, it will also equal to 1. So it will simply, my output will be like my input. So let's test it and see. Now, as you can see here, my input is 1. So again, I know that any change in the flip-flops will only take will only take place or change on the clock edge. So now if I change the clock edge, you will see that the output is like the input. It's not changing. When the input is 1, my output is 1. Now if I change my input to be 0, and now I add a clock cycle, you can see now that the output is 0. So now the JK flip-flop is simply working as a D flip-flop. So this would be the answer for the second exercise. It's very simple. And we verified that it behaves, the GK flip-flop actually behaves now like a D flip-flop. Now let's move to the last exercise for this lab. If we go back to the lab sheet, we will see that we've done with this question. It's very simple. And also the second question is even simple, very simple as well. And now we want to look at the last question. Now the last question might be a little like, it might be longer, but again, it's not hard. We've seen the steps in the other video. So right now we will just implement to design a 2-bit incrementing counter using a GK flip-flop, and we will see how will it work using Logisim. So let's go back to Logisim. And now I need, the first thing that I know, that I need 2 JK flip-flops. So we know that we need 2 JK flip-flops. So now I just want to remove everything and start from the beginning. It will be better. So I need 2 JK flip-flops. And since this is using synchronous counter, then both the clocks will be the same. So I'll need just 1 clock for both of them. And now if remember from the previous video, J and K, both of them are equal to constant 1. So now I will look for something called as constant 1. Where can you find it? Also, it's available in the folder that's called wiring. If you expand it, you will find constant. So you will drag it and add it here. Oops, this is the clock, so I need the constant. It's already equal to 1, so no need to change it. I'll keep it as 1. Now, we've also seen that I have 2 outputs, one from the first JK flip-flop and one from the second. So I'll add 1 here and 1 here. So now I know that J and K, that both the inputs are simply equal to constant 1, and the clocks are synchronous. So I'll just add the clock. Now the output for the first JK flip-flop is simply connected to an output pin. So I'm done with the first JK flip-flop. Now I can now look at my second one and start adding the inputs and outputs for it. But before I do so, let me label them so I can understand better what's going on. So this is my first flip-flop. So let me label it as GKFF1, which stands for JK flip-flop. And simply I'm saying this is the first one. And now I can also name this GK. number 2. And as we've seen, this is called Q0. And this would be Q1. Now, from the previous video, we've seen that J and K are simply equal to Q0. So I'll just take a wire and connect it to Q0, and K will also be connected to the same wire. So it means that J and K, both of them are equal to Q0. So let me write it here, J of the second one. So J, K here are equal to Q0, while JK here are equal to 1. And this is exactly the values that we got from the K map in the previous video. So now I know my inputs, I know my inputs here, my output here now, and finally I have another output here, and it will be simply connected to the output pin that I called Q1. So now we are done with connecting. If you remember something from the previous video, we've also mentioned that Q0 or output 0 will have the least significant bit. Oops. And Q1 will have the most significant bit. And since this is a 2-bit counter, so it only has 2 bits. And as we've seen, we have 2 outputs. Each one has 1 bit. So this is the 2-bit counter. So now this is simply a counter. So we are expecting that it will simply increase by 1, as we've seen previously. So it's a 2-bit, so it will just have 2 bits. So we have 0, 0, 0, 1, 1, 0, and 1, 1. Because this is a 2-bit counter, so each time it will be increasing by 1. So I always expected at the beginning to have 0, 0, and then when 1 is added, it's going to be 0, 1, and when we add another one, it's going to be 1, 0, and so on. It's simply a counter that's just increasing by 1 each time. When I reach to the final state, which is 1, 1, it's and I'm done with it, and then I also like add a clock cycle, then it will simply take me back. So it will just keep going through this loop starting from 0. So this is 0, this is 1, this is 2, this is 3. This is like in decimal numbers. This is the binary. So I have 4 states, and each time I'm increasing or I'm activating my 2-bit counter, and how by just simply adding a clock cycle, then it's going to increase by 1 till it reaches the last state. When it do so, it will go back to the first state. And this is how I designed it using Logisim. Now I want to try and see how does it work. Now at the beginning, I have 0 and 0. So my most significant bit here is 0 and my least is 0. So it's like I'm having 0, 0. Now, if I add by 1, I expect it to be now 0, 1. So let's try. That's true. So my most significant bit is 0 and the least is 1. So it's like I'm saying now it's 0 and 1. 0, 0, 0, 1. Now, if I add 1 clock cycle as well, what's happening? This is becoming 1 and this is 0, which is again verify the third state, which is 1, 0. And now finally, I expect it to be 1, 1. So let me try it. So now it's 1, 1. And now if I also add another clock cycle, then I expect it to go back to the first state. So it should go now to 0, 0. And this is exactly what's happening. So this verifies that actually I'm implementing it in the right way. And this is how we implement a 2-bit incrementing counter using GK flip-flops. So now for this lab, you are expected to take screenshots of the 3 experiments that we just did and then add them to the Word file and submit them. You have 4 days from today, which is more than enough. And if you have any questions or anything, let me know. All the best.